I just want to introduce our speaker, Rajesh Sundaresan. He's come here before and he's talked about various things like relief propagation and large deviations. Today he's going to talk about learning to detect an anomalous Markov process. Rajesh is an old friend of mine, and he's currently the dean of ECS and ISC. Somehow he finds time to do research. But he's done a lot of work starting from information theory, which was there's a famous result called bits through queues, where he had a different proof for his thesis using point process theory. And after that, he's looked at guessing, a lot of information theory work, and then also looked at local weak convergence for combinatorial randomized combinatorial optimization problems. He's done a lot of auction theory, mechanism design, some information design there, and some bandit work as well. So this is sort of related to it.
Thank you. Thank you for the generous introduction. Are you able to hear me? Are those online able to hear me?
Yeah, that's what I'm checking. Can you hear Rajesh?
Hello, mic testing. Can you hear me?
You're muted, I think, on that. Maybe you tried.
I'm deliberately muted.
Oh, because it doesn't work.
Just to be sure.
Okay.
The speaker speaks it off, so you should turn it on.
I have it on, yeah.
Prakash, are you able to hear me?
Yeah. Hi, Rajesh. I can hear you loud and clear.
All right, thank you.
Thank you. Hi, Vijay.
Hi, how are you? See you soon.
I'm well, thank you. See you soon.
Thanks for the introduction again. So I'll speak about learning to detect an anomalous Markov process. It's actually work in progress. There are some partial results that we have. And the one that we want to show is to have some gaps, and I'll highlight some of those gaps as well. Based on work done with the former PhD student, Ian Karthik, who is currently a faculty member at the Indian Institute of Technology at Hyderabad. Also, thanks to some generous funders, ANRF is
Agence Nationale.
sorry?
Agence Nationale?
No. It's equivalent to the National Science Foundation.
In France, right?
No.
Oh, here. Oh, sorry, India. Sorry, I got it. Yeah.
Okay, so here's the problem. The problem is one of trying to find what slot machines.
We just want to speak up a little bit. Maybe it's not totally clear.
Among 3 slot machines, 2 of them are identical. The third one is a little different. You can see that by looking at here, to identify which one of these 3 is the odd one. And the way you do that is by looking at measurements or whatever are the rewards that these machines are spewing out. The measurements come from the state space. The state space is a common state space for all 3 of them. Yes. Each of these is spewing out rewards in the form of a Markov process. The rewards form a Markov chain. And the transition probability matrix for the 2 that are identical is, let us say, P. And for the odd one is something that's different from P. Another transition probability matrix, Q. The rewards that come out when you pull each of these arms constitute a time series, which is a Markov process with this transition probability matrix. For the first one, it's x1, 1, x2, 1, and so on. The superscript 1 indicates the machine that it's coming from, the rewards are coming from. And the subscript indicates the time for the second one, and similarly for the third one as well. What are known in this particular problem? We know that 2 of the Markov chains, or the transition probability matrices that govern these Markov chains, are identical. And the third one, the odd one, has a different transition probability matrix. What are the unknowns? The unknowns are, we don't know which one of the 3 is odd. So the unknowns are gathered in this triple psi, which is a configuration or state of nature or the ground truth. We don't know which one of these three is odd. We also don't know what is the common for the two transition probability matrix, and we don't know the odd transition probability matrix Q. So the location of the odd one, the normal transition probability matrix, as well as the odd transition probability matrix are the unknowns in the problem. But you do know that two of them are identical and the third one is different. So here's the informal goal to find the odd slot machine. Identify the location of the odd slot machine as quickly as possible. And you should do this correctly with high probability. There are many applications. I got interested in this through a visual search application in collaboration with the neuroscientist, where the neuroscientist asked participants like us, the neuroscientist would show various images and there would be a drift in a direction. In a few images, the drift of the dots would essentially be in the same direction, but there would be one odd one. And it's sort of a Markov, it's executing a Markov process, the position of the dots. And how quickly are you able to identify the odd one, region where the dots were going in a different direction, gave the neuroscientist some hints about how our brain was working. And I came in to help with some visual search modeling for that particular problem in collaboration with the neuroscientist. But there are also other applications involving spectrum allocation, dynamic spectrum allocation, for example, or plane anomaly detection. So I'll not dwell on the applications today. I'll try to speak a little bit more about the perspectives about what are the difficulties in this particular problem. So more formally, we give a Markov decision process framework to this. So there is a history, HT, which is given by the action taken at time one, that is the decision maker pulled one of the arms, let's call that as A1. Then the decision maker received a reward, then a second arm, then a second reward, and so on, until you get to a time when you decide to stop and declare. What is a policy in this context? A policy is a set of action plans or contingency plans for all time, pi indexed by pi indexed by t. And pi t is something that depends on the history in this way. It tells the decision maker whether to stop or to continue. So that's stop or don't stop. And if the decision maker stops, it also tells which of the locations is the odd one. It prescribes a rule for the decision maker to tell where the odd slot machine is. And if it is to continue, if the decision is to continue, where to look for the next sample or which arm to pull. So just a little bit of recalling of notation.
Just a quick
Yes.
question. So you're choosing which to look, but do all machines, all Markov chains move or they're
Yeah.
rested?
So I'm going to speak about the most general setting where it will move,
Yeah.
but I will also speak about rested settings. Yeah. So the rested setting is easy. The restless is the one that's still open in some contexts.
Very question.
Yes, yes, please.
You are observing rewards. Are the reward functions the same across the machines and are they one-to-one?
No, they're not one-to-one. So each machine is independent of the other machines in terms of the rewards that they put out. So there's no correspondence of the rewards between one and another. The only thing that you know is that for two of them, they are identically distributed. That is, the process is identically distributed. So the processes are the same, but the realizations could be different.
So reward is a function of state.
Yes.
From state to
Yes.
distribution over.
Okay. So here is x1. When I pull the first arm, I probably got this one, x11, let us say. And then if this is the current state, your next reward is going to be something that depends on this. And that would be given by the transition probability matrix. So conditioned on you receiving x11, what's the distribution for the next one? You get some sample from that distribution. So it's one of the rows of the transition probability matrix.
So the rewards of the state and so.
So-
Rewards of the state.
Are you seeing state or are you seeing a reward that's?
Well, you can, rewards and states, I'm viewing them as identical.
So, yeah, make it partially observed.
Correct, yeah. So reward states for me are identical. You are able to see it in full.
Okay, that's
Thank you.
what I-
So Mingyan, you had a question?
So completely observed. When you sample it, yes.
Just like any regulatory, is it continuous or discrete state space?
Discrete and fine. I think conceptually this is difficult enough that we'll see. Okay, so just a little bit of recalling of notation. Here is this psi or the configuration or the state of nature captures all the things that we don't know. Where is the odd one? What's the normal transition probability matrix and what's the odd transition probability matrix? We have a policy pi, and what you see is going to depend the observations, etc. The law of what you observe is going to depend on the policy. So I'll not only include the ground state, but I'll also include the policy. I'll call that as the probability law for all the observations that you will see. And this is the expectation operator. So there are two performance metrics. The first one is how long do you take to stop and decide? And the second metric is when you decide to stop and declare something as the odd one, how accurate or how correct are you? What's the probability of making a correct decision that you have the odd one right? Or this one is what's the chance that you're incorrect, or what's the probability that you're incorrect? So you could make a hasty decision and optimize on how long you take to stop, but your probability of error would then be large. On the other hand, you could try to optimize this, but you might take a very long time to declare which one is the odd one. And so this expected time might be large. So what we would like is something that balances both, trades them off. There is a tension of them. The way we do this is we look at what are called epsilon admissible policies. So what are epsilon admissible policies? We want to bound the probability of error upon stoppage. So it's the set of all policies such that the probability of error upon stoppage, you declare something as the odd one upon stoppage, but this is the true one. The chance that you miss the true one is less than or equal to epsilon. And the point is that this must be true no matter what the underlying configuration. So this must be true for all psi. Whenever the odd one is different from the normal one, odd transition probability matrix is different from the normal. Now, this is quite demanding. The probability of error should not exceed epsilon, no matter what the underlying configuration. So the Q could be extremely close to P, yet I want the probability of error to be less than or equal to epsilon. And so that's demanding. The saving grace is that the expected time, whenever you have that situation where Q is very close to P, can be large, and you can deal with that. That expected time may depend on the configuration. Little bit of experience with sequential probability ratio testing, things that Wald had done in the late 1940s, would suggest that this expected time should go to infinity as epsilon, the probability of error, the target probability of error, goes to 0. And in fact, Wald, in the situation that he was looking at, also showed that this grows to infinity as log of 1 over the probability of error. So it goes to infinity as this plus some second order terms and so on. And when you divide the expected time by this, we actually try to capture as epsilon goes to 0, what the rate of growth is with respect to this log 1 over epsilon. And so our goal is to find amongst all possible epsilon admissible policies, this expectation infimized over all of these. But we know that that's going to be a difficult problem for each epsilon. And so we relax and ask for the rate at which it grows. By dividing this by log 1 over epsilon, we know it grows at that in that way with respect to epsilon. And we want to capture the constant front. And so we divide this and let it drive epsilon down to 0. So I hope this objective is clear. And so this is what we are after. So the way
Just
one
a
goes to solve this
quick
problem.
question
Yes, go
on
ahead.
that.
Yeah.
So, I mean, I guess, are you looking for, it's possible that the policy depends on epsilon.
It's possible that the policy depends on
Are you
epsilon.
looking for a universal policy or something that is asymptotically gets there?
So
Or
in this particular optimization problem and the limit that I'm seeking,
Yeah.
for each epsilon, the pi could depend on the epsilon. The
Okay.
optimal pi could depend on the epsilon if there is an optimal one.
Yeah.
But what I would like is only the growth rate.
Oh, so you just want to,
Yeah.
irrespective of policy
Uh,
characterization.
If you can give me a policy also, that would be good. And I'll highlight some policies. They are asymptotically, they achieve this in some circumstances, but not all. Okay, so I'll now, this is a good point to pause and ask if there are any questions, because the problem has been formulated. I now would like to step into how to address this question. So if there are any questions, I can try to address them.
So maybe ask, what is the policy here? It's like every time which out you choose.
Yeah. At each time, based on the history, you have to make a decision. The decision is to stop or not to stop. That's the first question.
Okay.
And if you decide to stop, you have to make a decision, another decision. If you decide to continue, you have to make yet another decision. If you decide to stop, you have to tell which one is the odd one. Remember that the goal is to find where the odd one is. So you've decided to stop, you're not going to pull another arm. Tell which one is the odd one.
And then if you decide to continue, you pull one arm.
You
and
pull,
then
yeah.
You observe the state of that arm.
You observe the state of that arm.
But
That will be
not the others.
not the other state. So you get to see only what you pull and not the others. And here, let me also add that there is a possibility that you can randomize your actions. To stop or not to stop could be a randomized decision. And once you decide one or another and realize that, which one you pick could also be randomized. So while I have indicated here, the pi t is sort of a deterministic rule, but you can also expand this to randomized policies. Allow yourself that flexibility.
So it's just another question. So are these Markov chains and your actions are picking which Markov chain to proceed, or are these Markov decision processes where you pick one of them and you pick an action of that as well?
So you have to, so the Markov decision process is you have to pick an action. What is the action? The action is which one of these I'm going to pull. So that's the action. So there are Markov processes, and I'm framing a Markov decision process on top of that, which involves all the three. Your action is which one you pick. Your observation is whatever is the next output conditioned on the state, depending on the appropriate law for that mission. So I hope that's clear.
Related question. So in the case of these chains, these arms are rested. It's simpler because you don't pull, they don't evolve. You just pull is the same as evolving, and then you see the state. In the case that these are restless, there is the distinction of activation transition versus in the natural transition without the activation.
So you're going to see that I'm going to
You
expand
can-
upon that. Yeah, I will deal with both of them and I'll speak about them. Thank you for the question. It'll come. Okay, so always in such questions, it's a good idea to not jump into perhaps what is achievable, but to ask what is not achievable. And that question is often answered through this sort of data processing inequality, which I try to highlight. I think many of you know about it. It's quite standard in this line of thinking. So the data processing inequality is something that says that processing cannot improve things. So look at this hypothesis testing problem where you want to distinguish between two hypotheses, P1 and P2, let us say. The observation X has a distribution P1 under hypothesis H1, and it has a distribution P2 under hypothesis H2. The X takes values from some alphabet A. So there is a certain performance for your hypothesis testing procedure that you would have here. On the other hand, you can think of maybe doing some processing. This processing here, I've sort of shown it to be deterministic, but it could be randomized as well. And then you can ask, once I get this process symbol, maybe you're trying to do some cleanup of the noise and so on. What's the capability to distinguish between the same two hypotheses, except that you have to look at the Y. The P1 induces a new distribution Q1, and P2 induces a new distribution Q2. So it's a hypothesis test between now Y, which is distributed as Q1 under hypothesis H1, and as Q2 under hypothesis H2. So can you do better with respect to this sort of a processing? The common sense tells us that you can't improve, because any processing that you do here, you can actually do the same processing on the left, and therefore there can't be an improvement in performance. And that's codified in this data processing inequality, which says that the relative entropy between P1 and P2, that's the relative entropy on this side, is bigger than or equal to the relative entropy on the other side. And this is what we are going to use to be able to say something about what we can't achieve, or a sort of limit on what we can achieve. So let's actually consider the ground truth psi, which has the odd location, the normal transition probability matrix, and the odd one Q. And we have a policy. Let's say that that policy is epsilon admissible. Now I can take another configuration, a challenge configuration. I'll call that psi prime. The important point about this psi prime is it has a different, possibly different transition probability matrix for the normal process, and a different transition probability matrix for the alternate, the abnormal one. But it's in a different location. And so these are unknowns. And if I have a policy which is epsilon admissible, and it does well when the ground truth is psi, well, if I challenge it with respect to this, then I should be able to distinguish psi from psi prime, because psi prime has the odd one in a different location. And so that's what I'm going to do. I'm going to test or challenge my policy, which is an epsilon admissible policy, with an alternative. And so here is what we do. Take an epsilon admissible policy pi. In fact, you can take it to be any one. The epsilon admissible policy, we will see how it pans out. I challenge it with psi prime, with the odd location being a different location, and I'll assess the performance. So the way in which I use this is I need to look at what the random variable on the left side of this box is. I need to tell you what the processing is, and I need to tell you what the random variable on the right side of the box is. So the one on the left side, I actually take all the things that I observe until the stoppage. That's what I call as X. So the action, the reward, the action, which arm did I choose, next reward, and so on, all the way up to this is the time prior to my stoppage. This is the time when I decide to stop. And when I decide to stop, I also choose which one is the odd one. And that's the L hat decision. So let me call this as X. Now, when I have the underlying configuration psi and the policy pi, that will induce a certain distribution. But the underlying configuration could be psi prime, and that will induce a different distribution for the same policy. What I do for the processing is I actually take this entire X and I focus only on the decision, final decision on where the odd one is. So Y is f of X is equal to L hat, the decision. So I'll write the probability law under the ground truth and this policy as P psi pi, and then P psi prime pi. Okay, so those are the two distributions. And similarly, you're going to get something on the other side for the decision, final decision. Again, it will be Q psi pi and Q psi prime pi for this policy. What does the data processing inequality tell us? Tells us that the relative entropy for this process on the left side, the X on the left side, which is this complex object, if you look at the probability distribution for this under the ground truth and under the alternative, that has a certain relative entropy. that's higher than what's on the other side, which is with respect to the distribution of just the decisions. The main idea is the following. Once you have this inequality, the main idea is the following. So that inequality, I have put it back there so that we can start off afresh in the slide. The admissible policy is something that distinguishes between psi and psi prime. And so you will see, and I'll show it in the next slide, what it means to be able to be epsilon admissible is that you're able to extract a certain amount of confidence from the system. There is information that you're gathering, and you're reasonably confident that this is the odd one. And that is measured, and it's measured in terms of certain units, which turns out to be log 1 over the epsilon. In some sense, you can call it the surprise associated with perhaps this being the odd one, and you need to be sufficiently confident that this is the odd one, that L is the odd. So,
Question.
yes.
Could you go back to the previous slide? So when f of x is the declaration, the decision made by this policy, what are these Q hypotheses? What are they?
So this will be a certain distribution on the odd one node. So there are three slot machines.
Yeah.
So L hat is going to be one of these. So it's just a probability distribution on the
They're
three.
the same one, right? No, wait.
They're not this. They'll not be the same for psi and psi prime. If you will, I will get to that. And so just a few more minutes. The next slide has it actually. So okay, so the policy extracts this much amount of information, and your question is what is cube psi and cube psi prime? It's a probability distribution on a set of three elements: arm1, arm2, arm3. It's just telling which one is the odd one, the decision that has been made. Under psi, you would have made a decision, and under psi prime, you would have made a different decision. They are two different probability distributions. That relative entropy is sort of what I'm calling as how confident or what kind of confidence you're extracting. It will become very clear in the next slide. So, but you need to extract this much amount of confidence. But on the other hand, there is a bottleneck. The bottleneck says that you can't get more than a certain number of units of confidence per unit time. Each time you sample, you can get only D star. I'll just say D star for that. And so if you have to, on the average, wait for this much time before you stop, and this is the amount of confidence you're able to extract per unit time. That's the relative entropy on the left side. That's that is lower bounded by this. I apologize. I'll say this again. So this is the relative entropy on the left side. That is upper bounded by the bottleneck times the number of time units that you need to go to. So that's the right way to say it. And so this relative entropy bound comes from the bottleneck. However, this is bigger than or equal to log 1 over epsilon. And from that, you gather that the expected time is bigger than or equal to log 1 over epsilon by t. So you need at least this much amount of confidence. In each step, you can get only D star. You have to wait at least this long before you can get the sufficient amount of confidence to make your policy epsilon. So the questions are, what are these bottlenecks per unit time? And how did this log 1 over epsilon come? Which I hope will answer your question. The next slide has that. So analysis of this. The interpretation of this cube psi is that it just gives the probabilities of the various decisions under the ground truth. If the ground truth is psi, under whatever is the underlying configuration. If the ground truth is psi, then what's the chance that you declare the first one to be the odd, second one to be the odd, or the third one to be? Under psi prime, it's exactly the same set of probabilities, except that if your policy is an epsilon optimal policy, it must be something that leads to two widely separated distributions. So let's see what those distributions are. Under psi, you have an epsilon admissible policy, which means most of the mass must be concentrated on L. All the others must have less than or equal to epsilon. But under psi prime, Well, your policy is epsilon admissible, it must be true, it must capture the correct one with high probability, even if the configuration is a different configuration, which means that your policy would put most of its mass on the other one, L prime. And so you see that there are two widely separated distributions now on this triple. And what's the relative entropy between them? So you can actually look at 1 minus epsilon by epsilon logarithm of that, multiplied by 1 minus epsilon. Epsilon by 1 minus epsilon, logarithm of that, multiplied by epsilon. And then for all the others, there's a third one also that you can take into account. The dominant one is the one that is over here. All others are of the order epsilon log epsilon or epsilon log 1 over epsilon. And so they vanish as epsilon goes to 0. The one that actually goes to infinity is here, and that's 1 minus epsilon. You can treat it as roughly 1 log of 1 divided by epsilon. So that's of the order log 1 over epsilon. So an epsilon admissible policy separates distributions under psi and under psi prime in such a way that they are far apart, more explicitly, more precisely. The relative entropy between them is log 1 over epsilon, at least log 1 over epsilon. Okay, so thus the relative entropy, which is what you have on the right hand side of the processing, is at least this much. Yes.
Previous slide where you were talking about the bottleneck, you mentioned that you cannot get more than this stuff. So the confidence you get, shouldn't that be on Q's instead of P's? Because the entropy of Q's, that is the where you make the decision, right? P's.
So the confidence comes from here that you need at least this much to be able to be epsilon admissible. But you see there is an upper bound here. And so somehow if you can get an upper bound on that, on the left, on the relative entropy on the left, then that gives you something like a bottleneck. So you have to analyze this to understand what the bottleneck is. That's why, so this inequality says that the relative entropy that you can get per unit time. So if I divide this by time, then you get T xi star as sort of being the bound per unit time. Okay, so we looked at log 1 over epsilon as the confidence that you should get. Now, where is the bottleneck and what is that bottleneck? So we need an upper bound on the relative entropy on the left side. So that's this. And I'm going to do the rested case first, so that it will be clear as to perhaps how to go about this. And then I'll speak about the restless and the challenges. So in the rested case, you can write down explicitly what the likelihood ratio is, and therefore the expectation of the likelihood, which is actually the relative entropy. And when you look at this likelihood and the logarithm of the likelihood, you go up to some time when you stop, and you can, thanks to the Markov nature of the observations, you can actually write them down as here is the configuration under psi, here is the probability of the sequence under psi, probability of the sequence under psi prime. Conditioned on the history, you took an action, what's the next observations probability? You saw something, what's the probability of observing that? But then there is also conditioned on the history, the action that you take. So this is conditioned on the action. So you should look at what is the chance of taking that action as well. That would come from the prescription or from the policy. So this one says on a per time step basis, the probability of an action given the history, and then the probability of seeing the observation that you saw, conditioned on the history and the action. So that's those two. And when you look at the alternative, what if you look at exactly the sequence and ask for the probability distribution, probability value under the alternative, you would get exactly what it would be under the alternative configuration. The important point here is that you have a policy that's independent of psi, which means that if you saw history ht minus 1, you have a certain action. That action is exactly the same as the action under the alternative configuration. That means that the probability distribution for the action AT must be exactly the same as the probability distribution for the action AT under the alternate configuration. And therefore, action is independent of the underlying configuration. You have the decision maker doesn't have access. And therefore, these two are identical and they drop out. of the calculation. And the important point here is I'm looking at the rested case. This is actually easy to write down because it's what you observe when you pull that arm on the previous occasion. And so that's exactly, here is when I pulled it on the previous occasion, that arm that I pulled on the previous occasion. What's the chance that I see what I see now? And I can write that down explicitly. It's just one step because the arms are rested. And I'll come to the restless case. And similarly in the other, or in the alternative configuration. This summation is basically counting instead of going all the way from 1 to the stopping time. It's counting in terms of which arms I pulled. So run through this in terms of the actions that are taken. And so it's just two different ways of counting the same thing, except that now each of the arms might have been pulled a different number of times. That's encoded in this NA of tau. At stoppage, how many times did I pull arm A? And this is what happens, this is the simplification that happens in the rested case. And when you look at what this expectation is, you can see that there is a random time here until which you run. And so this is something where you can use Wald's inequality, except that you have to generalize Wald's inequality for a Markov process. And that can be done. You can actually write this as the expected value of this multiplied by the expected value of NA of tau and summation. So this quantity on the left side, the relative entropy on the left side, is actually simplified to be equal to this, which you have here, expected number of pulls of arm A multiplied by a relative entropy. Now this relative entropy, so this is an expected value. There are two random quantities here. One is the, what did you see on the previous occasion? What are you seeing now? And the probability distribution of that. And when you run this enough times, this will concentrate to its expectation, which is actually the relative entropy conditioned on what's the frequency with which you see a particular value, so we are in a finite state space. What's the frequency with which you see a certain reward? That's given by this mu psi A. So mu psi A is the invariant measure on arm A. There's another way to see this as well. It's the number of times you enter into a particular reward or a state, and the number of times you exit, and they must match. They must match except for maybe the last one. That's where the approximation sign. And so
measure the, I mean, the two processes are different, though they have different invariant.
Yeah, so for each A, there is an invariant measure.
But that also depends on the.
That depends on the process. So
on the
for
psi or psi prime, right?
yes, correct. So that's why you have an invariant
yeah,
measure that
just with the
depends on
psi,
the,
okay.
yeah, it depends on the underlying configuration. But when you take this expectation, see the ground truth is psi. So the
Okay,
average will be
that's where it's
taken with
coming.
respect to psi.
Okay.
Okay. So I hope this is clear. And this says that you can actually simplify, if you normalize this by the expected time for stoppage, you can write this down as the fraction of time arm A has been pulled, and that's that I call as lambda probability distribution on the number of on the various arms. And therefore, what you have is that this relative entropy is approximately the expected time to stop multiplied by a certain quantity, and this quantity depends on the underlying configuration as well as the challenge side. For me to get an upper bound on this, the psi prime is something that I can choose however I want. And so I optimize, since psi prime is arbitrary, so long as it's on an arm different from psi. I actually take this to be as large as possible. So I optimize this. The optimization is the first thing that I do is I get my the information that you can get per unit time to be as small as possible. So I want, what's the bottleneck? To get to the bottleneck, I must squeeze the amount of information that the user or the decision maker is able to get. And so that's the inf. You won't be able to distinguish between psi and psi prime if you choose if you choose this appropriately. Not more than this kind of relative entropy between the two. But then as a decision maker, you can try to maximize for this worst case or nearest alternative psi prime, and that's the supremum over lambda. And so the D star, the bottleneck that you get to see is an arbitrary psi prime that tries to get this to be as small as possible, and an action plan for the decision maker that tries to maximize the amount of information that's obtainable. And therefore, that is an appropriate bottleneck. This says that this D, relative entropy on the left side, is less than or equal to D star times the expected. So that sort of highlights in the rested case the proof of the lower bound. Okay. So what about the restless case? The restless case is a little bit challenging because when we go and write down this, you can still write it in exactly this form, except that if you didn't pull the arm on the previous instance, the arm has moved. And therefore, you have to look at how many steps it has taken and then write down the appropriate transition probability matrix for something where an evolution has happened for a certain number of steps. And therefore, this is not correct. You can't just write XL minus 1 XL. And here, what one could do is write down something that takes into account for each arm, what is the delay between your previous visit and the current visit? So that's DA. And when you visited it on the previous occasion, what was the state? That is IA. And then, given that this is IA, what's the relative entropy between the two distributions when the number of steps that you have taken for this Markov process is DA? And so that's this relative entropy. And so you have to look at a slightly different one than the previous one, where you have to take into account all of these possible delays. And there are possibly large number of delays that you'll have to deal with. All of these have to be taken into account. Yes.
What if each time you play, you then continue for the renewal cycle?
You could do that. So you could keep pulling a particular arm until you come back to, let us say, something, and that will give you some observation. Then you switch to another one, and then you can keep pulling. So that gives you a lot of information to be able to gather the transition probability matrix of a particular arm.
Yes.
Right. So that's a good strategy from that point of view. But perhaps from an overall point of view, that might not be, because maybe
So it would be a worse bound, is what you're saying.
it would be a bound. It's a natural strategy, but it might not necessarily be the optimal strategy. So what is the optimal strategy is a question we need to address. Okay, so here, when I wrote this new of the arm and then this DA and IA, I can think of this as a new state in a lifted space. And this new of A, DA, IA as a state action occupation frequency in this lifted space. Yes.
I have a quick question. So in the rest of this case, like, when do the state observations happen exactly? Like, when you pull the arm, are you observing like the full state transition? So like its initial state and the state that it lands in? Or is it?
Okay, so when you pull an arm, in the restless case, you only see the new state.
You only see the new state.
Which means that maybe you pull that arm 5 pulls back. At that time, when whatever it moved into, you know that was the state. And in 5 steps, it has come to the state. You don't see the transition, you only see the current state. So that is, that's the way to view this. So you don't see a transition. If you see a transition, like for example, if an electron is moving from this level to this level, you would see that this is the energy that it's releasing, and so it probably came from here and jumped into this state. This is not that way. You only see that it has now moved to this. You don't get to see the photon packets or its.
And I guess another question is like, we're considering the case, like the most general case, where like the restless portion of the Markov process could be different between the two arms.
The restless portion of the Markov.
State evolution you don't have.
I didn't quite follow the question. Could you maybe
I'm just
Yeah.
making sure that we're dealing with the most general case.
Yes.
Where like,
Here we are dealing with the most general case.
So.
And
One quick comment, I guess you only lift it, you're taking it to a countable state space now.
yes,
Yes.
and
Potentially,
many
transient,
challenges.
transient, because I mean,
issues are
you
there.
want one of them to go to infinity, you're sort of pulling it many times.
Yeah.
Yes.
You want one of them to go to infinite. So if you want to learn this optimal state action frequency for you to be able to reach the bound, it can be a difficult process. But in principle, I can do the same thing as I did before. What's the nearest alternative, psi prime to psi? And then I can try to find out the best state action frequency, state action occupation frequency, and that's the new. You optimize. This is an in principle optimization. And again, I have the D star, which is the bottleneck in this new case, except that I don't have as simple an expression and as simple a probability law on just 3 elements on the previous occasion, but now it is something that's on a countable state space. So that's the challenge.
Plus that supremum was over a sort of an unbound, I mean,
Yes,
it's a
correct.
non-compact setting.
Correct. Yes. So I'm now going to say, try to say a few things about achievability in this lifted space. What we would actually like to do in order to be able to get, so here is this approximate, here is this bound that we had, and this is the bottleneck. D xi star is the bottleneck when the true configuration is psi. What we would like to do is, as much as possible, every unit of time, you should be able to get D star units of information, which means that, so D star is this, which means that you can actually turn this into a Markov decision problem, where you have to choose which arm to pull in such a way that you can take this to be the reward and try to maximize this reward. So it's a Markov decision problem that tries to get close to this per unit time. So a long-term average cost optimization problem where the reward is relative entropic in nature. There are many issues which I want to highlight. First is that you should be able to, we don't know the P or the Q. To be able to get to this, to be able to solve this problem, what's the optimal mu? You might need the P and the mu. And so there is an identifiability question that we need to address. You should be able to solve this with the relative entropic reward and be able to get this new, be able to identify what the new star is. That is ergodicity. So you should have ergodicity in the problem. And also at any point of time, you're learning these parameters. And the strategy would be that you would estimate these and apply whatever is the new star for that and sample according to that. That's called the certainty equivalence principle. The resulting new star that is induced is something that should be asymptotically optimal. That means that this new star is on an approximate one. It approaches the true parameters, but when that does, the optimal new star should also, new star for those must also approach the optimal one. And so that's a continuous selection problem. So we have 3 issues, and we'll have to see how to address these 3 issues: identifiability, ergodicity, and continuous selection. I just want to highlight how much time do I have?
About 10 minutes.
10
10.
yeah. I want to highlight
10-15 minutes because you started with the
I want to highlight a difference with regret minimization. In these kinds of problems where we sort of pull arms, learn about the arms, and then eventually identify where the odd one is, you actually have to sample each arm comparably often compared to the case where you're doing regret minimization, where the number of times that you pull, the fraction of times that you pull the correct arm approaches 1. So here you have to have non-trivial exploration. That's something that pops out. And so it's very different from what happens in regret minimization. Also, you're getting estimates of the Markov transition probabilities at each arm. These should go to the appropriate correct values as the number of observations grows. And so this suggests that the parameters are getting closer and closer to the true value. So if you understand the problem where you know the P and the Q, then we can solve the general setting also. So I'm going to restrict attention to the situation where we know the P and the Q and also an alternative. So here is a new hypothesis testing problem. New hypothesis testing problem is, I know the parameters P and Q. I know also if it is not P and Q, it's the alternative P prime and Q prime, except that the odd location can be different. So it's either this being the odd one, P being the normal one, and Q being the abnormal, versus another situation where the J is not equal to I and P prime and Q prime. So tell between these two. It's a simple hypothesis testing problem, and much of the complexity can be reduced to this. If we understand this, we'll be able to understand the general case.
Just a quick comment in the restless, there's a strategy that Mingyan was saying could be more useful, right?
We'll
In the
also,
restless case, because I know, I mean, I'm going to wait till you come back a renewal cycle. I'm only pulling one particular Markov chain.
Correct,
I have
yes.
no issues with. I
Hmm.
mean, you'll give you a lower bound, but that could be a.
So it would be a lower bound. The question is, we want to get to D star,
Yeah.
and there could be situations where that is a good strategy.
Yeah.
But there might be better strategies. Okay, so here is the broad strategy to get close to the optimum. The idea is, given that the odd arm is at a certain location, let's say I, and then the alternative is at J, a different location. Let's write down what the likelihood ratio of these two is and the log of the likelihood ratio. And so we write it as the natural logarithm of the likelihood ratios there. This is the likelihood of the observations and the actions under psi. This is under the alternative. And we consider perhaps maybe there are two alternatives, given that for psi I is the odd one, there are two possible values for j in the three arm case. And so in the general case, you take the minimum across all the possible references. And this sort of is taking the conservative approach of how far away I is, or how confident am I about I compared to the other alternatives, j. So the procedure is something that Chernoff had outlined sometime in 1959, I think, and it's he calls it procedure A. So I'll just call the policy as pi A. At the end of slot n, this is what Chernoff prescribes your action ought to be. Look at that Zi that I gave you, which is the confidence with which you think I is the odd one in terms of the log likelihood ratio. It's also looking at amongst the alternatives, which one is the one that's closest to I. So it's minimizing across j not equal to I. So call that as Zin and identify which one you're most confident about as the odd one. If you have sufficient confidence, that sufficient confidence is given by, you need to be eventually epsilon admissible. So epsilon must enter into the picture. So how confident ought you to be before you stop? You must have the log likelihood ratio to be at least logarithm of k minus 1 by epsilon, or the likelihood ratio to be at least k minus 1 by epsilon for the one that you're going to stop and declare as the odd one. If that is the case, then you take that and declare that as the odd one. That means that the evidence for this is overwhelmingly large, k minus 1 by epsilon, compared to the nearest alternative. Otherwise, if you're not confident about this, if you're not this confident, continue to sample. When you continue to sample, you should there is an odd one that you have as a candidate. That odd one will tell you perhaps how to sample. You have to solve this optimization problem, state action frequency. From that, you should be able to tell for this current history, this is the right way to sample. That is the solution from that optimal state action frequency. And that tells you which action to play once you disintegrate that state action frequency, and that's the lambda star corresponding to my star. So sample according to that. And when you do that, you will have the best chance to be able to get close to meeting this objective of gathering D star amount of information per unit time. In our case, what we need is a slightly different version of Chernoff A, one that maximizes one that uses not P and Q, because P and Q are actually not known, you have to estimate them. And so you have to use the maximum likelihood estimates for each hypothesis at the odd location, and it's not really good. So let me put down the assumptions again. The optimal rate at which confidence must be gathered is given here. Ergodicity will say that you're able to sample according to this mu. Identifiability says that as you sample, you will gather more and more information about the arms. Your strategy was to keep pulling it one after another. That will give you a direct way to estimate, but maybe there is another way to do it a little better. But then from that, you have to infer what the P and the Q are. And eventually those P and you should be able to approach the P and Q. So you should be able to identify, and there must be certainty equivalence. That is when you estimate the P and apply that, you will get a certain strategy. That strategy should be something that is close to the optimal strategy corresponding to the true parameters. So there must be a continuous relation to the optimal. So I'll skip this part in the interest of time. Why is Chernov's policy a feasible policy? It just involves a change of measure. It's a standard argument. I will skip this. I'll speak a little bit about modifications that you need to do to the Chernov policy to handle lack of information about P and Q. You're estimating those. So the way in which we handle the change of measure is to be able to do some sort of conjugate, an estimate based on a certain conjugate prior. In the case of the finite alphabet set, you can use a Dirichlet prior. And then you have the maximum likelihood estimate. So you reference the maximum likelihood estimate, but then you take for the numerator, for the I, something that is based on a conjugate prior, and then you compute the posterior. And that gives you the Zijn. If you do this, you're able to essentially meet the epsilon admissibility that is there in the previous slide. Just take this for granted because it is connected to the previous slide, which I skipped. And then do exactly the same thing, but for this modified likelihood ratio, where you are comparing the likelihood ratios with the corresponding to the one that's closest, the nearest alternative location. And the modified Chernoff procedure A is essentially to do exactly stop at the situation where the likelihood ratio is sufficiently large and declare that one as the odd one, otherwise continue to sample. And when you continue to sample, you choose the lambda star that corresponds to the estimated parameters. So let me say a little bit about previous works and when lower bounds and upper bounds match. So this is a strategy to try to achieve that bound. The lower bounds and upper bounds, one can show that they match when instead of Markov process, we actually have IID observations. They also match when things are rested. And they also match when things are restless. However, there is no learning. You don't have to learn the P, you don't have to learn the Q, you know them. I mean, all that you're trying to figure out is where is the odd one, okay, which arm is odd. In all of these cases, the approach that I highlighted actually achieves that. There's a certain bottleneck. That bottleneck you will be able to extract that much amount of information with modified Chernoff procedure. And these are based on some works that several have done and some that we have also done. Our ongoing effort, though, is beyond these to which we made some contributions to be able to handle the unknown P and Q, and in a situation where we sort of induce ergodicity by bringing in a trembling hand for the person, the decision maker. So the decision maker, the way in which you can induce ergodicity, but that ergodicity is induced with some loss in performance, is whenever you want to pull a certain arm, you go towards pulling it, but by mistake, you might pull another arm. So if you have that sort of a trembling hand, then that gives you the necessary ergodicity. And this is a parameter that you can drive down to zero And for any positive parameter, you have ergodicity, but when you drive it down to zero, that's when the challenge is all the way. So here is a summary with which I will stop. What we have in the most general framework in the restless situation is only a lower bound. For the learning to detect the odd restless Markov arm, we can show that the expected stopping time, the tau is missing, grows to infinity, and it grows to infinity at least at the rate 1 divided by d star times the log of 1 over epsilon, where this d star is given by this abstract soup-inf optimization problem. And in some special settings, the IADK is the rested Markov, and the restless Markov where the P and the Q are known, you don't have to learn them. This bound is achieved. However, in the most general case, it's still not working. With that, I'll stop.
Any more questions?
Yeah, so.
Hi, may I ask a question? This is Prakash.
Yeah, please.
Narayan. Hi.
Go ahead. Yeah.
Hi, Rajesh. If instead of identifying the odd arm, the player was asked to come up with a distribution. In other words, the output that the player has is a distribution which puts probabilities on the different arms of being the odd one out. That should follow from this in a straightforward way, right? From what you said, the
Instead
lower
of
bound.
Yeah, instead of probability of error, what
Yeah.
you're probably looking for is maybe a distance of the distribution that I put out with respect to perhaps where the true one is.
That's right. And the other question is, what would that distribution be? What properties should it have? So here you have a point mass, right?
I have a point.
If instead you wanted a distribution and postulated some requirements on that distribution, can this approach be followed? From what I could see, at least up to a point, you could. I'm not sure about the last part.
I think the relative entropies between Q and the Q prime, I'll just call that as Q prime, the nearest alternative. Up to that, if your distances are in terms of these relative entropies, or the divergences are in terms of these relative entropies, this
Right.
will automatically apply.
Okay.
Have some other distance measure, then you might choose a different measure of distance or divergence, which has a similar property of data processing inequality. And that might all the steps that we have would apply to that as well. So I think,
see.
for example, if the distance is something which is an Ali-Silve distance, they all satisfy this data processing inequality.
That's true.
Be able to carry things forward.
Okay. All right.
But I haven't thought about that, but yeah. So
Okay. Thank you.
Yeah,
Thanks.
Yeah, just I want to ask if I understand correctly. So this is the lower bound result, and do you have any idea to design any at least heuristic policy that works?
Yeah. So that policy comes from the Chernoff policy. So I'll just go back to highlighting that. So here, let's go to this. So what we try to do is at each instant of time, let's call that as n is time. We try to identify which one is the one where I have the greatest confidence. And how do I do that? The Zi is the likelihood ratio or the log of the likelihood ratio of I being odd versus the nearest alternative. So there are confidences I have or the likelihoods I have for alternates, which is the one that comes closest to I. So that ratio at the logarithm of that, I call it as Zi. So for each I look at its nearest alternative and I look at that ratio, logarithm of that. I call that as Zi. Which one is the one for which the gap is the largest? That I call as I star. Now I will stop. This is the policy. This is the program that you should follow. You should stop when that log of the likelihood ratio is sufficiently large, or the likelihood ratio is sufficiently large. How large? For it to be epsilon admissible, it must be at least as large as k minus 1 by epsilon. This k minus 1 comes from one wanting to beat a union bound. So, but it should be of the order 1 over epsilon, and k minus 1 will help you beat the union bound. If it is that large, then you stop and declare this as the odd. If it is not, then you sample. And when you sample, you should sample according to some distribution that gets you as much information as you can per unit time. So let me go back to that. You should be able to sample in such a way that per unit time, on the average, you're able to extract d star units of information. For that, you have to solve a Markov decision problem where you have an entropic cost.
Yeah.
And the entropic cost is a long-term average. This is the state action occupancy measure. And this one sort of tells you the long-term cost associated with this entropic. I wouldn't call it cost. I'm actually trying to maximize this. I would call it a reward. You're extracting information. So you should maximize the reward that you get. So that means that the lambda star should be such that it's matched to this. It's aiming to get this d star. Remember, d star is the bottleneck. You have to get as close to d star as possible. Now, how do you do this? I say as close because soup in
Yeah,
that's why
this computation is feasible.
it's not feasible. it's an infinite dimensional optimization problem. So this is an in principle approach. If you're able to solve this and get the state action occupancy frequency occupation measure, then you know the history, you know the DA, IA, so you can disintegrate this and identify what the distribution of A corresponding to this state is, and that's your lambda. So you'll take the action according to that. Now, your question is absolutely valid. Is this something that you can actually compute? This d star as well as this nu. How can you compute? The only difference that I have is that you can, if you can compute, then you'll be able to get close to this. And in these situations, you're able to reach that. That is in the IID case and in the rested Markov case, and as well as in the restless Markov case. In the restless Markov case, it's computationally hard. So the challenge of computation is present here. However, in the IID case and in the rested case, it's a finite dimensional optimization you can solve. Yeah. So here it's an in principle optimization.
Yes, that's
And
why.
and
yeah,
you hope that you can
have you
reach.
test on the 3 machine example is 2 identical, 1 different, and
So
the rest is
yeah, so this is, you can do it. Rested you can do.
the rest is
Even for the restless, you only have a proof with computationally it's difficult. Yeah.
Yeah, but I think it's interesting. And try like the
What you could try is maybe some sort of features, and you could learn on those features and up to that. But whatever those features can tell you about what the optimal policy is. But yeah, it's a computationally hard problem. But you could use some modern approaches to attack that and come close to that. Maybe some neural net based approaches, which can try to manage the complexity to some extent. But yeah, I'm not worried about the actual computation. In this talk, I was more focused on in principle.
yeah.
Any requirement on irreducibility, right?
I don't have any requirement on irreducibility. But if it is there, it helps because ergodicity would come as a consequence. And it's ergodicity that sort of enables. So this is actually a long-term average cost optimality criterion, or in this case, average reward optimization criterion, where I have this entropic reward, relative entropic reward. And to be able to achieve this, if I have ergodicity, I can try to attempt to get these averages converged to this. I don't per se need irreducibility, but if there is irreducibility, there is
Just impacts the quality of the
correct.
balance.
Yes.
Another question on that. So here, you're basically trying to do a multi-step transition probability.
Yes. Correct.
As the step that gets large, probably deteriorates, right?
Yes.
So it's basically
It's
Also
closer
back to
and closer to the
stationary.
stationary distribution.
So
you could use that to simplify. I think that's perhaps the point. that you're
But
making.
intuitively, with that in mind, your sampling, I view the restless problem mostly as an uncontrolled, and you're just making observations. So I think that was simplified. There's no pulling and activation. You know, the action is which one to observe, right?
Which one to observe, yes.
Yeah,
I mean, the action of pulling is irrelevant here. Which one you observe?
So with that in mind, the way you sample, I guess, what would be intuitively good strategies that if you do you have any sense of what that near optimal strategy might look like?
So, let me go back to the rested case, but what you want is something for the restless case, because that's the one which is challenging. But for, I can say something about the IIT case and something about the rested case, but I don't know a good strategy. I haven't thought enough about that. So let me go back to the rested case, and then the IIT case will also be clear from there. So pardon me for going back so many steps. Okay, so previous slide should have. So in a sense, the D star is actually given by this optimization problem. And let's look at the situation where it's IID first. IID means that you don't have to worry about this stationary distribution. You don't have to worry about the conditional distribution. It's just when you sample that arm, what reward are you likely to get? When you sample the other arm, what reward you're likely to get? Here, interestingly, the lambda A is, as you get closer and closer to becoming more and more confident that one of them is the right one, you should sample according to a certain fixed distribution, lambda A. You can forget the history. You just have to, if you're close to, let's say, arm 1 being the true one, you have to pull the other arms too. You have to pull them in a non-trivial fraction. You have to pull them non-trivial fraction of time. But there's a fixed probability distribution with which you will pull. And that comes from this relative entropy. Sometimes it's to pull this arm itself and verify that this is indeed what this is the correct value. But sometimes it's actually beneficial to pull the other arm. So you get to see that the other arm is different. And the important point here is that this lambda A is a fixed distribution. It doesn't depend on the history. So that's an observation that you can make. And this optimization problem is easy to solve. It's you just have to find 3 parameters here in the case of 3 arms. And it's this is something that we can compute numerically for most examples. When you look at the restless case, something interesting happens. Again, you don't have to worry about the history. If you think that this is the odd arm, then you have to sample that, but independent of what you observe. That's another thing that simplifies. Not so when you go to restless. When you go to restless, you lift it to this infinite dimensional space of countable state space. And it's not clear what is happening. So what are good strategies in this circumstance? The one that you highlighted is a good method that will help us come up with a good way to compute, because your what is the maximum likelihood estimate when you see 2 steps or 3 steps later of the transition probability matrix? There isn't a good way to come up with the P when you don't have control over the time steps. A good way to control that is you keep observing one after another and then switch to the next one. So when you do that, there's a natural maximum likelihood estimate. But if you don't have control, sometimes it's 2 steps, sometimes it's 3 steps. Come up with the best maximum likelihood estimate. For me, I don't know the computation scheme for that. So it's not clear. And your approach is a good approach from a computation perspective. But I suspect that there are better approaches you have to search for.
So I had one question. This is, if you look at Chernov's
Procedure
Procedure A.
A.
It
Imaginatively
looks like an index rule in some sense on
Yeah,
on the general.
correct, yeah.
So, and if you search through index rules, is there a way of identifying what would be a good, I mean, because you need, I mean, usually for index rules to work, you need some value function to have some properties and stuff there. I mean,
Well,
can you even say that an index rule is optimal in this context?
Well, what Chernoff has said is that this is the index that you should compute.
Yeah.
I think computation of the index is not the difficult one.
No, yeah.
Right, so because the computation of the index involves just computing the likelihood.
Yeah, no, what I meant in the class of policies, should I just work with index policies or should I work with something else? Because
Yeah, I mean, this particular one is an index policy,
yes.
but the challenge here is not one of an index policy. The index is here. The
This is one
challenge
index policy. This is one
This is
index.
one index policy,
Yes.
but the challenge is one of having identified this as the odd one. Which arm are you going to pick next? That's the computation problem. That involves computation of the optimal state action frequency and identifying the appropriate probability with which an action should be picked for the state. That's where the challenge is.
No, I was thinking in terms of if you look at your general Markov decision process in the restless case as well.
Okay.
And for that problem, at least under some conditions, can you say that an index policy is optimal?
There is a question of optimal. This is only asymptotically optimal.
Yeah.
Because remember,
that's right, epsilon optimal. Yeah.
But index policy is optimal.
No, but it's only in the cases where you know you have the.
I think maybe I misinterpreted what you said. I interpreted the index to be the one that is the odd one.
Yeah.
But what you're saying is pick this arm as the index.
Yeah.
But no, I would say that that's the arm to pull, and you're indexing that. I think that's what.
Yeah, that's what I'm saying.
No, I don't think that's the right thing to do.
Okay.
Because when you do that, you will only pull one of the arms because the probabilities, etc., will all be.
Well, I'm talking about. So typically index policies are deterministic, but I don't know if there's a randomized version of it.
Here, I know that you have to pick the other ones in a non-trivial way. The other arms in a non-trivial, because after all, what are you doing? You're looking at the statistics and you're comparing whether they are the same. Yeah. And you're checking that this is different from the other. So you have to pull the arms and not.
You have to use randomized policies.
So from that perspective, from the point of view of picking an arm, index policy would not be the approach.
Can you randomize it according to the ratio between these?
Yes. So that is what I interpreted when he said index policy, that you pick an index for an arm and then you randomize
based on
in an appropriate way based on that index.
Yeah.
Then that will work. That's what the
Chernoff was doing. The other,
which is what I interpreted.
But that's I was going. I was going to say that next, but then I think that's what you. The other one, one of the computation here looks like the Sanoff exponent for Markov chains, but it's probably not the same.
It is not because see, there's a difference between Sanoff and these are stopping problems.
Yeah, that's
Sanoff usually comes when you're looking at a fixed horizon, and the Sanoff theorem is for that
fixed
end, and there is a way by which you can do that. So the optimizations here will involve its optimization of one versus the other. So in the relative entropy. Sanoff, so we can.
I'm just.
So this wouldn't be Sanoff, but it would be wall
type of
sequential probability.
Any other questions? Let's thank Rajesh.
Thank you, sir.
And thanks everyone for waiting online.
Thank you, Prakash and
Prakash
others are there. Others who are there.